Hello and welcome to a lecture on Fundamentals of Electromagnetics. My name is Steve Ellingson. The purpose of this lecture is to give you a refresher on some of the fundamentals of electromagnetics. These are all things that you perhaps have seen in a previous course, your first course in electromagnetics, for example, or perhaps something in the course that you're taking now. But the purpose is not to take the place of another course, but simply to give you a reference, a concise listing of some of the things that are important. So here we go. First, a list of topics. First thing I'll talk about is materials, and specifically how we characterize materials in electromagnetics. Talk about electromagnetic sources, primarily charges and currents. I'll talk about electromagnetic fields, in particular the electric and magnetic fields. I'll talk about boundary conditions. I'll talk about Maxwell's equations, of course. I'll talk about the creation of fields, the various ways in which we can cause electric and magnetic fields to come into being. And then finally, I'll talk about frequency domain electromagnetics. Up to this point, we'll be talking in the time domain, which is kind of the most natural way that most people think of this. But frequency domain electromagnetics is where we really do most of our work in engineering applications. This goes by other names, time harmonic electromagnetics. We use phasor quantities, and I will discuss briefly on this topic. Okay, characterization of materials. First, permittivity. We describe this using the Greek letter epsilon. We give it units of farads per meter. You might think of this as the ability to store electrical energy, the ability of some material to store electrical energy. In that sense, you can think of it as the point form of capacitance, although capacitance is more of a larger scale term, refers to a structure. Whereas here we're talking about a property of a material. So there's a distinction here. In free space, the permittivity is 8.854 times 10 to the minus 12th farads per meter. And we describe other materials in terms of relative permittivity, epsilon sub r, which is the multiple of the free space permittivity that that material has. Typically, epsilon sub r has values between 1, which would be free space, up to 6 or 9. Some materials maybe up to 12 to 20. Typically not much greater than that for non-exotic materials. Second parameter, permeability. This is given by the Greek letter mu. We express it in henries per meter, in other words, inductance per unit length. And you can think of it as being a point form of inductance. In free space, the permeability is 4 pi times 10 to the minus 7th henries per meter. And like with permittivity, we express the permeability of other materials as some multiple of the free space permeability, mu sub r. So for most materials, mu sub r is 1, the same as in free space. For certain other materials, such as ferromagnetic materials, the relative permeability can be quite high. Tens, hundreds, thousands, and so on. For most materials, though, that are not ferromagnetic, permeability, the relative permeability, that is, will be about 1. Then conductivity. We give this the Greek letter sigma as a name. We give it units of Siemens per meter. That's reciprocal resistance per unit length. This is a relationship between the electric field and the current. In that sense, you can think of it as a form of Ohm's law. In fact, it is a very general expression of Ohm's law. You can think of it as the point form of conductance, or the point form of reciprocal resistance, if that is helpful. Of course, in free space, there's no free charge, so the conductivity is 0. If you have no free charge, it doesn't matter what the strength of the electric field is, you have no current. Conductivity of a perfect conductor is infinite. Permittivity, permeability, conductivity, these are all referred to as the constitutive parameters of material. Constitutive parameters. Material is said to be homogeneous if its constitutive parameters are independent of position. By that we mean you can imagine some block, some chunk of material. If you pick some point in that block and you determine its constitutive parameters, you will find that the constitutive parameters values are the same in any other point that you pick. That's a homogeneous distribution of constitutive parameters. We say a material is isotropic if its constitutive parameters are independent of orientation. So you could take that same block, you could identify a face. Here's one of the faces. If it's isotropic, it doesn't matter how I've oriented that block. So I could rotate the block so that that face is now up here and measure the same point in space, and I would find the same constitutive parameters. Most normal materials are isotropic. A famous example of a non-isotropic material would be something like quartz. In quartz, the constitutive parameters are very different as you rotate the material in space. Material is linear if its constitutive parameters are independent of field quantities. That is, for example, the permittivity is independent of the electric field. If the permittivity depends on the electric field, then the material is most decidedly not linear. Again, we can come up with an analogy to circuit analysis. If you have a capacitor, the capacitor is considered to be linear if the capacitance is independent of the potential that you put across it. If, however, the capacitance changes as a function of the potential you put across it, then it is not linear. Now, there are other stronger conditions that we could potentially apply to this. They normally do not arise, but you should be aware that there are other stronger or perhaps even weaker conditions that we can put on materials in order to say that they're linear or not linear. Material is lossless if its conductivity is negligible. So, for example, free space has conductivity equal to 0. It is therefore lossless. As the conductivity becomes significant, we say the material is lossy. So the loss we're referring to here is the tendency of electromagnetic fields to be converted into current, specifically electric field to be converted into current. And then finally, we're going to assume that media are time invariant. In other words, if a material has certain constitutive parameters now, the material will have the same constitutive parameters seconds from now, hours from now, and so on. That's not formally required, of course, but most analysis we will assume that, and it will greatly simplify the work. Sources. First, electric charge. We give this the symbol rho sub v. That v is a indication that we're talking about the volumetric electric charge. That means the charge in a volume. So this has the units of coulombs per meter cubed. We refer to this as the source of the electric field, and specifically the source of the static electric field. So if you recall in your first course in electromagnetics, where you first encountered this, you undoubtedly did many calculations where you had a distribution of charge and you calculated the electric field in response to that charge. Of course, there are other ways to arrange charge other than volumetrically. You could have charge distributed over some surface, some sheet, for example. You could have charge along a line, like so. And you could just have just a point charge. There's a positive charge and there's a negative charge. In those cases, then we would describe the charge distributions differently. This would have units of coulombs per meter squared, coulombs per meter, and this would just be coulombs. The second source I'd like to discuss is the electric current. We give this the symbol J, and it's a vector. It has both magnitude and direction. And in general, it has units of amps per meter squared. So the way to think of that is you have some boundary in space. There's current flowing through that boundary. So that meter squared is referring to the area of this opening through which the current is flowing. And then you have so many amps flowing through that opening. So amps per meter squared. The electric current is a source of the static magnetic field. So currents give rise to magnetic fields. And of course, there are other configurations. So for example, I could have a surface current. I can have some surface here, which I'll attempt to draw, and I could have currents running along that surface. Now, the way I would describe that as so many amps per meter, how many amps is flowing across some line. So this has units of amps per meter. And of course, I could have line currents. Here's a wire, for example, and it's carrying current. There I just have amps. So different ways to describe the current. But again, the most general way to do it is in terms of amps per meter squared. Of course, there is no such thing as magnetic charge, as far as we know. So we don't need to discuss that. And there's also no such thing as magnetic current. However, there's a little bit of discussion we need to have there. This concept of magnetic current is sometimes invoked not because it actually exists, but rather as a useful way to represent fields in certain situations. So, for example, in discussions of apertures, where, for example, you might have some opening in a sheet, you may have some electric field in this aperture. It turns out to be very useful to convert this electric field into an equivalent magnetic current. Now, how we do that is an advanced topic. So, fields. First field to consider is the electric field intensity. That's a vector. We usually give it the letter E, the symbol of the letter E in a capital. Has units of volts per meter. Volts per meter. So how much potential is incurred by traversing a certain distance. The related quantity is the electric flux density. This has the symbol D, also a vector. Has units of coulombs per meter squared, and is actually defined as the electric field, volts per meter, times the permittivity. So the electric flux density is a way to kind of commingle the notion of electric field intensity with the permittivity of the media that field exists in. Magnetic flux density, capital B, it's also a vector. Their common units include Tesla or also Webers per meter squared. Webers, as you may or may not know, Webers are units of magnetic flux. So it makes sense. Magnetic flux divided by meter squared, which is area, gives you magnetic flux density. So again, magnetic flux density, either Tesla or Webers per meter squared, either one is fine and commonly used. And in fact, there are other units that are common for magnetic fields as well, but not commonly used in engineering electromagnetics. Magnetic field intensity, H, is a very closely related idea. It's defined actually as the magnetic flux density divided by the permeability of the material in which this field exists. With a little math, you can find that this gives you units of amps per meter. Amps per meter. So again, it's kind of a commingling of the idea of a magnetic flux density with the permeability of a material. You can think of the electric field E and the magnetic field B as being fundamental. These are things, for example, that a physicist could relate to. In fact, most physics is done using those two quantities, at least classical physics. These quantities of D and H are not really fundamental. You can tell that right away because they're not independent, right? Once you know the electric field intensity and you know the permittivity, then you know the electric flux density. So they're clearly not giving you any more information. However, they're useful for notational convenience, and that's one reason why we really like to use them. And then in certain cases, such as nonlinear media, they become important. If, for example, mu is a function of B or H, then you can see that there is no longer a simple dependence between those two quantities. In fact, you may recall curves that look like this, where you have H and then B, and you see some curve like that. You can also define vector potential fields. These are also not fundamental. They provide no additional information, but they're very useful relating sources to fields. Boundary conditions. A boundary condition is simply a relationship between the electric and magnetic fields at a boundary between two media. So for example, in this picture, we have region 1, which has electric fields E sub 1 and H sub 1. And then over here we have region 2, which has electric fields E sub 2 and H sub 2. And at this boundary, we may or may not have current, electric current density, and we may or may not have surface charge. The way we can figure out what the situation is using the boundary conditions. So for example, here we have the boundary condition on the magnetic field intensity. We find that the normal, which is defined to be into region 2, cross with the difference between H2 and H1 on S, and remember this is a boundary condition, so it applies only on the surface, is equal to the surface current density. You can see from simple dimensional analysis here that this has units of amps per meter, right? So this is a surface current. And has units of amps per meter. Another way of describing or saying what this equation means is that any discontinuity in the tangential component of the field intensity must be supported by a surface current. So if you have a discontinuity across in the tangent component of H crossing a boundary, there must be a surface current there to support it. Similarly, here we have a condition on the electric fields. It says that the normal component of the electric flux density across a surface, this has a discontinuity, it must be supported by a surface charge density. Remember, units here of coulombs per meter squared, right? So any discontinuity in the normal component of the electric field, the electric flux density must be supported by a surface charge. If you don't have a surface charge, then the normal component of the electric flux density must be continuous. And in fact, any other condition you can imagine, you must have continuity. Now, of course, there's an important special case here, which region 1 is a perfect electrical conductor. In other words, the conductivity in region 1 is infinite. So in the case where the frequency is anything other than 0, then we know that in a perfect conductor, there's no magnetic field. So H1 is 0. And we find this. So N cross H2 must be equal to the surface current. In other words, that discontinuity in the magnetic field intensity must be supported by a surface current. Similarly, D1 is 0 in a perfect conductor. The normal component, therefore, of the electric flux density must be equal to a charge density. That means if you have a perfect conductor, and you have a non-zero normal component of the electric field on that conductor, then you must have a surface charge to support it. And of course, if you've ever done a parallel plate capacitor problem, you know this. Finally, there's this condition, which is really no different than what we've already said here, but this is the famous expression E tan equals 0. In other words, on a perfect conductor, you can't have a tangential component of the electric field that's anything other than 0. And this is just a mathematical way of saying that. Okay, now Maxwell's equations. First, the Maxwell-Faraday equation, which I will perhaps refer to as MFE, the Maxwell-Faraday equation. This is a relationship between time variation in the magnetic field to spatial variation in the electric field. This is a generalization of Faraday's law and is also related to wave propagation. Here we have Ampere's law, which says that time variation in the electric field is related to space variation or variation in space of the magnetic field. So interesting symmetry between these two equations. And then, of course, we find that this is where current comes in. So current as a source of fields comes in through Ampere's law. This is Gauss's law. Gauss's law says the divergence in the electric flux density is equal to the volume charge density at that point. So it's a relationship between electric fields and electric charge densities. And then finally, Gauss's law, but now for magnetostatics, it says the divergence of the electric flux density is equal to zero. Sometimes it's paraphrased as saying that there is no particle or no point source that gives rise to magnetic field. Remember, the source of the magnetic field is a current. Source of the electric field is charge, and only charge can exist in point form. So what we have here is 4 simultaneous partial differential equations. Just as with any partial differential equations, they can, in principle, be solved for the fields. So if you know J, if you know rho sub V, you can, and you know the boundary conditions, which I've just told you, you could solve for E, H, and then also B and D, because B and D, of course, are very simply related to E and H. Note that these are the time domain expressions, that is, the physical real-valued quantities. I make that distinction because in a moment we will do the frequency domain expressions, which are a little bit different. Also, note that these particular choices of fields eliminate explicit appearances of the constitutive parameters. What do I mean by that? Well, I've chosen to use E and B here, and those are fundamental, and that's great. But here I've chosen to use H and D, and the reason is because that conceals the constitutive parameters. Now, that's just notational convenience. It's really a preference. There are many other ways to write Maxwell's equations. Some people prefer to write them all in quantities of E and B. Some people prefer to use E and H and D. I mean, there's nothing, none of these are necessarily wrong. It's just one way to write them. Okay, creation of fields. How do we obtain an electric and magnetic field? Well, you know from electrostatics and magnetostatics how to do this. For example, the source of the electric field is just static electric charge. You have some charge density, it immediately gives rise to an electric field, and you can compute that using Coulomb's law, for example, which, by the way, comes from Gauss's law. If you have a steady current, then you have a magnetic field, and it's straightforward to compute that. You can use the Biot-Savart law, which, by the way, comes from Ampere's law. The key point here, or something to keep in mind, is that for statics, when the sources are non-time varying, you have only static electric charge and steady currents, then the electric and magnetic fields exist only when their associated sources exist. In other words, if you turn off the static electric charge, electric field disappears. If you turn off the current, the magnetic field disappears. And you can have either one or the other. They can exist independently of each other. The situation becomes more complicated when things are not static. So, for example, when B is time varying, you can make E. This is Faraday's law. For example, if you take a magnet and you move it around a coil, you know that you can create a potential in that coil. Similarly, if the electric field is time varying, you can create a magnetic field. This is the essence of Ampere's law. So another way to create a field is to vary the other field. If you want to create an electric field, you can vary a magnetic field. If you want to create a magnetic field, you can vary an electric field. So this is the principle behind motors, generators, electrical transformers, and other devices. A third possibility, which is really not that much different, but it's a distinction that is useful to make, is that accelerated electric charge leads to coupling between electric and magnetic fields. First of all, you can note from Maxwell's equations, we go back here, that we already see that E and H, the electric and magnetic fields, are coupled. One changes in one gives rise to another. That is, if there's a time variation. So the moment there's a time variation, there's a coupling between these electric and magnetic fields. And the interesting idea about that, or the interesting consequence of that, is you no longer need a source. So if you have electric fields and they start varying, they become coupled and they can become sources for each other. In other words, you can think of the electric field as a source of the magnetic field being a source for the electric field. Another way of thinking about that is just to call it what it is, which is propagation. So, in other words, changes in current in J create the electric field and magnetic field. And then the coupling between the electric and magnetic field is responsible for the radiation of power. The beautiful thing about this is then you can turn off the source, and that electric and magnetic field will continue to remain coupled and will carry away the power associated with that source forever. All right, very different scenario than what happens in the static case. Okay, frequency domain electromagnetics. For many problems which are not either electrostatic or magnetostatic, then we prefer frequency domain representation. So what do we mean by that? Well, what we mean is that we consider the response to a sinusoidal excitation at an angular frequency omega, right? So we assume that whatever source we have, it has contained within its mathematical description a factor that looks like cosine omega t or cosine omega t plus phi, just to be more general. And we keep omega as an independent variable. All right, so we do the analysis assuming a sinusoidal source that has that form, and then we keep omega general, and then we find out what happens. That way we can change omega, and we can find out what the new response is, and so we get a frequency domain representation. This is also known, primarily in older books, but still the term is sometimes used, time harmonic analysis. So sometimes you'll hear this referred to as time harmonic analysis, but it means the same thing. It's just frequency domain analysis. If the media, that is, if the materials are linear, recall the previous assumptions that go into this, then the response will also be sinusoidal. This is a property of any linear system, not just in electromagnetics. If the system is linear and the excitation is sinusoidal, then we know that the response will also be sinusoidal. So this is a very powerful idea. We know in advance that just as long as the system is linear, if all the sources are sinusoidal, then whatever excitation we get out of it will also be sinusoidal, and it will be at the same frequency. So this is a tremendous help in doing analysis. If we can decompose problems into superpositions of sinusoids, then we can take those sinusoids one at a time and run them through the system, find out what the response is at that frequency, and then we can put together all the results. That's superposition. So it's a very powerful idea. As a result of this, there's no loss of generality in frequency domain electromagnetics. The frequency domain and time domain scenarios are related by the Fourier transform. So it's if you have the frequency domain representation, you can take a Fourier transform, get the time domain representation. This is all very, very nice. In other words, the frequency response is the Fourier transform of the time of the impulse response, just as it is for any linear system. Okay, so when we talk about frequency domain electromagnetics or frequency domain anything, this topic of phasors comes up. This is really a very basic idea in electrical engineering, so I'm sure you've encountered it before. But just to make sure we're on the same sheet of music, let's say a little bit about this. All sinusoidally varying quantities not only have the same omega in a linear system, but they can also be described using just two quantities, and that's magnitude and phase. Right? If I have some quantity, a cosine omega t plus phi, I know omega is not going to change because of the linearity of the system. The only two things that can change are the magnitude a and the phase phi. So these quantities are referred to as phasors. A phasor is simply a complex valued constant whose magnitude is the magnitude of the waveform, and whose phase is the phase of the waveform, but I can represent it using a constant. So the phasor representation of this quantity would simply be a e to the j phi. All right, same magnitude, same phase, but now I can represent a waveform, something which is varying with respect to time, as a constant in the frequency domain, a e to the j omega phi. This is a very powerful idea. To get the physical, that is the real valued quantity from the phasor, you just multiply it by e to the j omega t, take the real valued component of the result. So for example, the real part of A e to the j phi multiplied by multiplied by E j omega t is this. So we get the real part of A e to the j phi plus omega t. And that's just A cosine omega t plus phi. It's what we started off with up here. So I say that for two reasons. One is you should know how to get the real valued waveform out of a phasor, but also don't forget that this is what we're actually talking about. That's the physical real valued quantity. This phasor is just a way of thinking about what's happening. It's a mathematical convenience. It's not the actual physical thing. It's just a representation of a time-varying thing. Okay, so now that we've talked about phasors, we can put Maxwell's equations in phasor form. Let me show you what these look like. There's a Maxwell-Faraday equation. You will note that the only difference here is this. I'll come back to that in a moment. Here's Ampere's law, Gauss's law, and Gauss's law again. Again, this is for electric fields. This is for magnetic fields. First, just let me note that I'm using the same variables to represent the time and frequency domain quantities, so be alert to this. Here, all the field quantities are phasors. In other words, they're these complex valued constants, whereas in the previous time domain expression of Maxwell's equations, the exact same symbols were representing time-varying quantities. So this is perhaps a little bit sloppy, and some authors would go to special links to use different symbols in either case. But that gets a little bit tedious, so I will rely on you to stop and figure out whether we're talking about phasors or time-varying quantities as we go along. Second thing is note that derivatives with respect to time have become factors of j omega. And this is one of the beautiful things about phasor representations. In the time domain representation, this was differentiation with respect to time. Now, I don't know about you, but given the choice between differentiating something and multiplying something by j omega, I'll take multiplication. So this is a tremendous mathematical simplification. It's eliminating one layer of calculus that we'd ordinarily have to deal with. So very nice simplification. That concludes this lecture on fundamentals of electromagnetics.